All right, good evening, ladies and gentlemen. This is the first of a couple videos that I am posting for these optimization problems. This is problems 1 through 20 from the textbook. I will try to get the other ones up a little bit later. So let's just go ahead and get started. Most of these you've probably done already, but this is just for solutions and how you can do the problems. So question number 1 is the finding numbers. Now, because you have the textbook, I'm not going to write the problems up here, but I'm just going to go through the problem themselves. So you're finding, you know that the sum of two non-negative numbers is 20, and you want to find the numbers for A. The sum of the squares is as large as possible and as small as possible. So kind of a two-parter for problem A. So I know the sum of two numbers is 20. Now, when we do these problems, we're only allowed one variable, so I know that y is equal to 20 minus x, and that helps me out. So question A, it says the sum of the two numbers, or sum of the squares. So I have x squared plus y squared, but y squared is actually 20 minus x squared, is equal to some function, just f of x. And we need to find where is this the maximum, where is this the minimum, or as small as possible or as large as possible. Now, what you'll need to know is, first of all, the domain here is from 0 to 20. So we have endpoints that we're going to have to test along the way. All right, so if I do the quick math here, I get my function f is actually x squared. If I FOIL this, this becomes plus another x squared minus 40x plus 400. I simplify this to 2x squared minus 40x plus 400. I can now take the derivative of this function. So this is f of x. I can take the derivative of f of x, and I get 4x minus 40. And I want to know, when is this thing equal to 0, because I'm looking for a critical point. And I get x is equal to 10. So I have critical points of 10, 0, and 20. So I have to test all of them. So I know that f of 0 is, all right, so 0 squared plus 20 squared. So 0 squared plus 20 squared is 400. I can do f of 10. F of 10 is 10 squared plus 10 squared. Well, that's just 200. And I could do f of 20 is equal to 20 squared plus 0 squared, which is 400. So for question A, it says the sum of the squares is as large as possible. Well, as large as possible is if I chose the number x to be 0 or 20. So my large as possible is 400. And my smallest is the 10 and 10. All right, so that's question A. Question B is one number plus the square root of the other is as large as possible or as small as possible. So for question B, if I actually wrote B there, is the number plus the square root of the other. All right, so x plus the square root of 20 minus x is now my new function h. And if I took the square root of this, or not square root, the derivative of this, h prime is now 1 plus 1 over 2 radicals of 20 minus x, the negative from the derivative of the inside. I could combine these two fractions. This 1 is super easy to change. It just has to change to this denominator. So it's 2 radicals 20 minus x over, actually all over, with the minus 1, 2 radicals of 20 minus x. Now, in order to find critical points, same ideas occur. My domain is still 0 to 20. Only now the other critical point comes from the 0 of the numerator. So I look at the point let's go 2 radical 20 minus x minus 1 equals to 0. I add 1 to both sides, and I take divide by 2 equals 1/2. Therefore, 20 minus x equals 1/4, which tells me that x is equal to 19.75. So my critical points are 0, 20, and 19.75. And if I just did the values here, h of 0 is 0 plus the square root of 20, which is approximately, I don't really even care. What is that? 0. What is the square root of 20? Let's see. I might as well find the decimal here. Square root of 20 is 4.47. H of 19.75 is 19.75 plus the square root of 0.25, which is, the square root of that is 0.5, so I get 20.25. And h of 20 is equal to 20 plus the square root of 0, which is 20. And you'll notice, weirdly, the maximum shows up at this slightly less than 20. So here's my max. Here's my min. My minimum is at x equals 0, and my y is a value of 20. Here, my x is 19.75, and my y value is 0.25. Okay, so straightforward on this particular problem. All right, moving forward. Number 5. Number 5 is the inscribed rectangle underneath the triangle here. There's a little figure in your book there, and it tells you, first of all, for question A, to represent or express the y-coordinate in P in terms of x. So first of all, I need to write an equation for line AB. Well, nicely, line AB is on an isosceles triangle, and there's some right angle stuff, which means the equation is actually just 1 minus x. So the coordinate for P is actually x comma 1 minus x, because that's how high it is. Well, that's actually super nice for us because question B says express the area of the rectangle in terms of x. So area with respect to x. So first of all, the base is not x, it's actually 2x because it's 2 lengths away from the origin there. And my height is just 1 minus x. So I get a very nice function of 2x minus 2x squared. And then what is the largest area? Okay, so largest area comes from derivatives. So a prime of x is 2 minus 4x. I want to know when that's 0. So 4x equals 2, x equals 1/2. So my area, I'm looking at the area of 1/2 is equal to, and you'll notice here that there's really no endpoints because endpoints here create an area of 0 in both cases. So the endpoints are not necessary for us to test, even though you could test them just to make sure you understand that. And I'm going to get 2 times 1/2 times 1 minus 1/2, which is 1 times 1/2, and therefore my maximum area is 1/2. And dimensions are 1/2 by 1. All right. Again, problem 5, not too difficult. They do get obviously harder. All right, problem 9. Problem 9 is the river problem with some fencing. And I'm going to draw a picture for this one because it's kind of nice to see the picture here. You have some river running along here, and you have a fence that you want to find the maximum area of. You know these side lengths are x, and you know this side length is y. And you want a max area with a given 800 meters of fencing. So you know that 2x plus y has to equal 800, and therefore y is equal to 800 minus 2x. Again, we just go straight forward to writing an area problem using only x values. So area is just x times 800 minus 2x. And I could find the derivative of it straight away or just get the quadratic here so it's a little bit easier. 800x minus 2x squared. Therefore, a prime of x is 800 minus 4x. I set that equal to 0. And therefore, x is 200. The other thing you got to remember is that's not actually what the question is asking. And it says, what's the largest area and what are the dimensions? Well, the dimensions are 200, oops, not 2,000, 200 by 800 minus 400 because the x value is 200. So 200 by 400, and the area is 8 with 4 zeros. All right, easy peasy. Problem number 12. So these start getting a lot nicer here. Problem number 12 is the catching rainwater problem, and you have an 1125 cubic feet cuboid, I guess is what it's called, rectangular tank with a base of x and x. All right, so here's what you have. You have a rectangular tank with a square base, and the square base is x by x with a height of y. Now, you know that the volume is equal to 1125, so it'd be nice to know an equation for volume. So volume is length times width times height. So I get x squared y is equal to 1125, but I have to do the same thing as always. I have to get y in terms of x, so I can create other equations where I only have x values. All right, so we're going to take that c equation that you have there, and we're going to find c prime. Actually, we're going to look not at c prime first. We're going to actually look at c itself. And we're going to substitute the y value that we just found here because we can't do it without the y value. All right, so we get 5x squared plus 20x times y, which is actually 1125 over x squared, plus 10 times x times y, which is 1125 over x squared. Sorry, I kind of ran out of room here. Harder to write with these things here. All right, then I'm going to simplify this a little bit so I can find the derivative a little bit easier. I'm going to say it's 5x squared plus, the x's cancel, I get 2250 over x plus 11250 over x. And guess what? I'm going to go even a little bit farther. I'm going to combine all of this together. I'm going to put this over x, so I get 5x cubed plus 22750 33750 over all over x. Now I can find c prime. C prime is going to be a little bit easier in this particular matter. C prime is going to be 15x squared, the derivative of the top, times the bottom, minus the derivative of the bottom, which is 1, times the top, all over the bottom squared. If I simplify this numerator down a little bit, I get 15x cubed minus 5x cubed, and I get 10x cubed minus 33750 over x squared. If I want to know when this thing is equal to 0, I'm going to set the numerator equal to 0, so I get 10x cubed minus 3375 with a 0 on there equals 0. I get x cubed equals 3375. And the cube root of that, I get x equals to, let's see, what did I get here? 15. That means I'm kind of done. My x value here is 15. This x value is 15. And if I did this 1125 divided by 225, I get 5. So I get a volume or a dimensions of 15 by 15 by 5. Okay, moving right along, problem 17. We're looking at designing a can. You can read the problem for yourself. Obviously, you have some sort of volume that you know, and we're going to use that right away. I know volume is pi r squared h, and I know that's equal to 1,000. So I need h in terms of r, so I'm going to do this really quick. I'm going to say it's okay, it's 1,000 divided by pi r squared. And I'm going to use their area equation that they have. I have an area equation of 8r squared plus 2 pi r h. Well, h is now 1,000 over pi r squared. Simplify this down, I get 8r squared plus, that's 2 times 1,000 is 2,000. The pi's cancel, one of the r's cancel. I get 2,000 over r. I can combine these things by creating common denominators. I get 8r cubed plus 2,000 over r. I can take the derivative of this now if I so choose. Well, it's what I want, actually, not that I so choose it. But a prime is going to be the derivative of the top. So 24r squared times r minus the derivative of the bottom, which is 1, times the 8r cubed plus 2,000. This is obviously not the only way to find the derivative here, but it's just the way I chose to do it today. Create a little arrow to come up here. I get, for my numerator, I get 24r cubed minus 8r cubed, which is 16r cubed, minus 2,000 over r squared. I want to know when this thing is 0, so I want to know when is the numerator equal to 0. And I get r cubed is equal to 2,000 divided by 16. I get 125. Oh, that's nice because 125 is a cubic number. So r is equal to 5. Well, what does that mean for us? You have to make sure you understand what that means. R is 5, which means we need to figure out height as well. Because actually the question says, where's it at? It says, what is the ratio of height to radius? So we need to find a ratio. So height is equal to 1,000 divided by pi times 25, which is r squared. That's this h, remember? And this is equal to 40 over pi. Well, I want to know the ratio of height to radius now. So I get 40 over pi over 5. And this comes out to a ratio of 8 over pi. And I know the book says 8 over pi to 1 because it just does. It's a ratio of this number to 1. All right, keep moving forward. Number 19. Number 19 is the designing a suitcase problem. Now, I'm not going to do all the letters for this particular problem, but I will do most of them. So for question A, it says write a volume equation with respect to x. All right, so the volume being, this one's kind of challenging. But in that particular picture, I'll do my best to draw this picture here. It's kind of bad, but it's okay. All right, so in this particular spot right here, this is the base of my suitcase. And in this little corner right here, we cut out an x and we cut an x here, which means the length of that piece is 2x. The length right here is going to be the original width, which was 24 minus 2x. And the length of the box is going to be 18 minus 2x. Now, that might have taken you a little bit of time to wrap your head around it. It took me a little bit to wrap my head around what the length of the base was. But then the most part, it just came kind of to you, because I've done these problems a lot before, and I've kind of seen these types of problems, and you're always taking a distance minus some sort of cut out value. But I like these type of problems. You know that already. All right, so that's volume, but I want to make it a nice cubic here, so I'm going to multiply everything together, and you can verify this for yourself if you want. This formula becomes 8x cubed minus 168. 168x squared plus 864x. So question B is find the domain. Well, domain is, well, x could be 0. And the largest that x could be is actually 9, and it has to do with this piece right here. If you got any bigger than 9, this width or length or whatever you want to call it really doesn't make any sense anymore. So my domain is 0 to 9. And that should technically be pretty obvious to you, because if you went to 12 like this one, this length would be negative, and that doesn't make any sense. Question C says graphically, so this is a calculator problem. Do that on your own. You could use this, you use this function to find a maximum volume using your calculator. All right, but I like to do this analytically, meaning find the derivative, that sort of fun stuff. So v prime of x is equal to 24x squared minus 336x. Notice I actually did multiply by 2 again, rather than that one debacle that I had the other day. All right, so I get 864 there at the end. Now I want to know when this thing is 0. Oh, this looks so ugly. But what's nice is this 24 can actually come out of my problem. And I want to know this one is 0, so it gets 24 times x squared minus 14x plus 36. Now, this is not a non-factorable problem, so I have to use quadratic formula. So x is equal to 14 plus or minus the square root of 14 squared, I don't care, plus or minus, whatever, minus 4 times 36, all over 2 times a. 24, remember, doesn't make any sense in this problem anymore. And if you simplified this down, I can let you go with that. You can figure that part out for yourself. 196 minus 144 is 52. So I get 7 plus or minus radical 13. And I know you can do that, so you can verify that for yourself. Now, this is equal to 2 different numbers, as you know. So 7 minus the square root of 13 is 3.39. And 7 plus the square root, oops, messed up my calculator. 7 plus the square root of 13 is 10.6. 10.61, actually. But this is outside the domain, so it doesn't make sense. So my maximum volume is going to occur at 3.39. All right, and then you can plug in 3.39 into your volume function to figure out what the maximum volume of your suitcase is going to be. All right, and then for question E, I'm going to do a little trickery because I'm going to use some answers that I already have previously. And question E just says find the volume where it's equal to 1120. So I'm going to take 8x cubed minus 168x squared plus 864x equals to 1120. I'm going to subtract 1120 from both sides. Kind of follow along here. Nicely, 8 gets to come out of all of these things. What do I get here? Minus a 21x squared plus 108x plus, oops, sorry, minus, I think I know what I did with my ones in there. Minus 1120. Minus 140 equals 0. Now here's where you're going to lose. I'm going to use a little trickery because I've already solve this, this actually factors to x minus 2, x minus 5, and x minus 14 equals 0. Now, technically, in this particular equation, x equals 2, 5, and 14. Now, again, 14 is outside the domain, and you'll notice that these are the only two actual solutions. So if x is 2 and x is 5, you could create a suitcase with the volume of 1120. All right, let's get number 20 out of the way. This will be the last one for this particular video. Hopefully the others will come up soon as I get them finished as well. So number 20 is the quickest route problem, or route, I guess, if you like to say that word. Jane is sitting 2 miles offshore, so she is somewhere out in the water out here. So here's Jane. She is 2 miles offshore, and there is a straight shoreline, so that's kind of weird. Straight shoreline that is 6 miles in length down to the village, so the village down here. If you connected this, she is directly offshore, which means it's a right triangle, which means there's just a lot of math that you can do here, obviously. So there's a couple little things that you got to do. So first thing, if we just want to kind of figure out, okay, so she says she can row at 2 miles per hour, and she can walk at 5 miles per hour. So let's just think if she went directly back to shore and directly down the shoreline. So 2 miles, and she can travel 2 miles an hour, and then 2 miles per hour. Actually, I'm going to get rid of those units. I don't need all that. I just want to figure out how long it's going to take her to travel just going the direct route. So 2 divided by 2 plus 6 divided by 5 is going to equal 2.2 hours. Pretty easy math. That was pretty easy. Or what would happen if she just rowed? Well, 6 squared plus 2 squared is 40. So this is the square root of 40. That's the length of this if she just rowed down to the village. Well, if she just rowed down the village, she would take square root of 40. Oops, that's ugly. Square root of 40 over 2, because that's how fast she rows. And the square root of 40 divided by 2 is 3.16. So it's going to take her 3.16 hours to row only and 2.2 hours to do a direct route both directions. But here's the thing. That might not be the shortest time period. So she's going to row at some point down here. Now, the whole length is 6, but she wants to travel some x units away from here, and she's going to travel 6 minus, or it's going to be 6 minus x this direction. So this length here is 6 still, only now she's going to travel x units away. She's going to travel some unit down there. This particular length is going to be x squared plus 2 squared. So x squared plus 4, if I actually wrote that in there. Now what? Well, this is the weird piece here. I mean, like, what are we actually trying to find? We're trying to find how far down the thing she should travel. That's going to create a minimum amount of time. So it's going to actually be the length of that dashed line, which is x squared plus 4. Now that's going to be a rowing thing, so you have to divide by 2 to figure out length. And then you're going to have to add 6 minus x divided by 5, which is how fast she walks, which is equal to her time function, how long it's going to take her. Well, that technically means enough information now to find the derivative. So I can find the derivative here. The derivative of the first one is relatively ugly, but not bad. If I look at this as a fraction, the 2 stays in the denominator. A 2 comes from the square root piece times the square root of x squared plus 4. And the derivative of x squared is 2x. Well, that's kind of nice. And then, no, it's not nice. It's ugly, but it's doable. Then the derivative of this is just going to be negative, what, 1/5? Well, that's super nice. So what can we do here? We can get rid of one of these 2's. Oh, I like this eraser button because I can get rid of that 2, and I can get rid of that 2. And then I can combine denominators or combine fractions here, and come on, give me what I want. There we go. All right, so this needs a 5. This needs a 5. This needs a 2 radical blah, 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 and a 2 radical blah, blah, blah. So I can say I now have a new thing for my derivative that is 5x minus 2 radical x squared plus 4 all over 10 radicals of x squared plus 4. Now that's my derivative function. Now the problem comes is how to solve this. So I'm going to do some trickery, right? No, not really. I just want the numerator equal to 0. So I get 5x minus 2 with the radicals equals to 0. I'm going to subtract 5x and divide by negative 2. So I get the square root of x squared plus 4 is equal to 5x over 2, or 5 halves x. And I square both sides. If I square both sides, I get x squared plus 4 is equal to 25x over 4. I think I'm going to have to erase a little bit of stuff so I can get a little bit of room here. Almost done with this problem, so kind of bear with me here. Let's go ahead and get rid of this picture so I can use this spot over here. All right, so my picture goes away. Oh, all those little dashed lines right there. All right, so I get back my pin, and it tells me that x squared plus 4 equals 25x over 4. I'm just going to get rid of that dividing by 4. So x squared, where did I get x to the 4th from? Jeez Louise. Not even paying attention. All right, x squared. 4x squared plus 16 equals 25. Something's not coming out how I wanted it to. So where did I make an error? Let's see. 2 makes 5, 5x. Oops. I made a big error here, I think. That's what I get for not following my notes, huh? All right, so let's see. 4.5, number 20. No, 4.4, number 20. Let's look at the right problems here, Mr. Nelson. Am I doing number 20? Okay, I'm going to have to exit out of this really quick. I'm going to look at my solutions manual. I hope I have that open still. Number 20, what did I mess up on? All right, so you notice here that you have basically the same thing that I had here. I had a number that I just kind of messed up on, so on this particular piece here, you should get x is equal to plus or minus the square root of, plus or minus 4 over radical 21. Somewhere I think I just accidentally put a wrong number. And you'll notice that we can discard the negative value, and this, the 2.2 we got from before, the 3.6, 1.6 is what we got before, and you'll notice this 2.12 is actually the shortest distance, the positive, or the shortest time, and you'll notice that if she went 0.87 miles down the shoreline, she would get to the nearest, the shortest distance, or shortest time period. All right, sorry about that mess up. I had the problem correct, and then somewhere along the line I messed up a number. Hopefully you can tell me where that was afterwards. All right. There's the first 20. Hope to get the next ones up soon. I can't guarantee it when, but I will get them up as soon as I can. All right.